Okay, I think we'll get started. Fun day today. We're going to be using the LuckFox to go out to the internet and pick up real-time data. In particular, we're going to be tracking the position of the International Space Station. So there's a free API that developers can use to just request latitude, longitude, timestamp information about the International Space Station. Then we'll calculate the ground speed of the space station and then display that on an OLED. If you're coming to us right from the rest of the series, everything should be set, although I will talk about the Python packages that we're using. But if you are coming to us new for just to this video, then this builds upon a couple of other things. One, we have to get the Python, we have to get Ubuntu installed on to the LuckFox, and the LuckFox tutorial does a great job of that. Also, very good video by Fusion Automate on YouTube that goes through how to set up your LuckFox with Ubuntu. In fact, all the labs that we've built with in this series have started after the installation. Our lab number 1 in this playlist goes through the different Python packages, more than we need for this, but that will include many of them. And then I believe it's lab 5 on our OLED labs, another package that's needed to make the font on the OLED look nice. So with those, then you should be all set. All right, so what are we going to do? Well, as I mentioned, we're going to display the real-time position, and we're going to calculate here a ground speed. So what does that mean? What is the position and what is the ground speed? So obviously, the International Space Station is in orbit above Earth. This is about 400 kilometers. And so what we imagine is that a line normal to the surface of the Earth coming up and incident upon the International Space Station. If we look at the latitude and longitude position on Earth, where that line originates, where the normal line originates. For our formula, we'll use phi for latitude and lambda for longitude, and then as reference, the radius of the Earth is a little over 6,000 kilometers, and we're going to need that to calculate the ground speed based on changes in latitude and longitude as we go out and gather the latitude longitude data. So our LuckFox will call the API. The API will send the information sent back will be in a JSON type format, and in there will be latitude, longitude, and time. Then we'll need to cull that out, and then we'll calculate the ground speed and display that on the OLED. I'm not going to get into the programming. I just had Gemini whip out the programming. One-shot deal. It worked really easily. So we'll talk a little bit more about some of the basic calculations, and then also about setting up with the LuckFox. Okay, so to do this, this was a fun one for me because I've never really used this formula. This is called the Haversine formula, and it's used often in navigation on the globe for calculating the distance for small changes in latitude and longitude. And apparently, it's a bit more robust than other methods. So there's something called defined as this Haversine of x. Well, that is just shorthand for the sine squared of x. Oops, there should be an x here. Sine squared of x over 2. So we have the Haversine law of cosines, so somewhat analogous to the law of cosines, that relates this parameter c to, or at least the Haversine of the parameter c, to the change in the latitude and longitude, or the latitude between 2 points. So if we want the distance between this point and this point on Earth along the Great Circle, then we have phi1 and phi2. So we'll take the Haversine of the change in latitude and longitude, then cosine of each of those individually, and then that multiplies the Haversine of the lambda, which is the longitude, so the change in the longitude. Okay, well, to pull out then the c from this, so this formula will give us the Haversine of c. Another function we don't see all that often, and that is the 2-argument arctangent, a tan 2, and this is just a somewhat of a convenient function to help keep track of what quadrant a point is in. So if we have some point here, if we take the arctangent, the natural branch of the arctangent will give us a point in this, would give us the point in this quadrant. But let's imagine we had just the inverse of that, and we're over in this quadrant. The arctangent is the ratio of y over x, and we would get the same value. So if we just use the arctangent, we would get the value of this angle, but then we'd have to keep track separately of the quadrant. This just does that automatically by keeping track of the signs of each of the arguments. This is the y coordinate, and this is the x coordinate for that point. All right, then it's just a matter of, we've got this angle, and then that's along the Great Circle. So then we have to multiply by the radius, and that will give us our distance formula for change in latitude and longitude along the Earth, along the Great Circle. Okay, so then our API is going to grab time, latitude, and longitude. And we can go out and grab that at any interval we want. So we'll just grab that at a set interval. We'll get time, latitude, and longitude. And from that then, we will use this formula to calculate a change in distance, and we'll use the time information to get a change in time. So the first point will be just the first point, but then after that we'll take the ith point minus the I minus 1th point in terms of the latitude, longitude, and time, and we'll be able to calculate then a speed. So by way of comparison, the International Space Station orbits about every hour and a half, so it's really, really whipping. That's hard to even really imagine. And so it takes just over an hour and a half to circle the Earth. If we calculate the circumference of the Earth, that's 40,000 kilometers, and then if we divide by 1.55, we get a prediction of about 25, just under 26 kilometers per hour. Now, this is not the speed of the space station itself, because that's up off of the Earth. This is the speed of this sort of shadow cast on the Earth as it goes around. So that's called the ground speed. Now, it turns out we're going to be a little bit short of that. Not exactly sure why that is, but obviously there's different precision in the the Earth is not perfectly spherical, and there's some round off here. The other thing I noticed is that I don't know if it's just fluctuation in the formula for calculating the longitude, or for calculating the latitude and longitude that then sent back through the API, or just a natural variation. Obviously, it's not a natural variation in the space station itself, but these numbers will fluctuate kind of up and down as you watch it over time. All right, so with that, let's go to the computer and get this going. Okay, so I'm here in the terminal, and I'm in my projects directory, so you could go wherever you want to put your files. And so let's just grab our file. So first thing we'll do is just get on the internet, go to Google, and then Darren Olness, and it'll be likely this first one, wheretheiss.at. And let's go to our page for this series. So the LuckFox microcontroller. And we're going to go down to International Space Station Velocity OLED. It's saved here as a text file, but it's actually a Python file. So just go ahead and grab this whole thing. Now, let's go back to our terminal and go sudo nano, let's call it ISS speed.py. And we'll paste this in. And again, I'm not going to go through all the details. Gemini wrote it very quickly, one-shot deal, didn't have to change anything. Gemini, I've noticed, is rather verbose, which is good in a sense. It really handles errors. It puts a lot of comments in, but the code gets a little bit longer. But in terms of learning, either you do it, get it done because you're more focused on the hardware, or it's good that it's really well written out, because then you can kind of see everything. And so we're not going to go through everything, but I do want to hit these imports. So again, if you're new, a very common package is request. This is going to be anytime you're writing a Python program to go out to the internet. And I believe it's the most downloaded Python package. JSON, system, signal, math, and time are all just standard libraries, so you don't need any of those. If you go back to our video on the OLED, then we'll see that we needed this Luma package to make the fonts look nice. So at least on my OLEDs, the fonts are very hard to read if you just use the base font. So these Luma-based packages are necessary. And then Pillow is needed, surprisingly, I guess, for actually generating those fonts. So we need a combination of Pillow and Luma for that. Now, the other thing the only other thing that I really wanted to talk about here was this API call. So let's see where this is. So this looks like some website, and it is. So let me close this, and let's go to, it's called wheretheiss.at here, and gives a tracking of this, and basically calls this API the same one we're going to call to get the latitude and longitude. Okay, so where do we find that? So we just go to this site and then go down to API, and here is that same site we're using. So we'll make a call to this site. So let's go back here. This is exactly this right here is what's right here. Now, the satellite ID is 25544, and so that goes right here. And so that's what this line is doing. The rest then is making that call, grabbing the JSON file, pulling out what's in the JSON file, and I think that's down here. So we can see here a response So this is the call right here, and then this is the response. So we're going to be able to pull this, and pull time. Where's time? Timestamp right here. And notice it does have a velocity. And if you look at this velocity here, 27,000 kilometers per hour, that is the velocity of the space station itself, not of the ground velocity. Just check a couple of facts here on Wikipedia. So I kind of mentioned this, but we can get a little bit closer. The orbit here, about basically 93 minutes. So really whipping, and then the speed, I think there's a velocity here. Maybe I'm missing it. But it's on the order of, right here. So 27,600. Okay, so we're going to get a number less than that. And we're actually going to get a number that's a little bit off of what I had on the whiteboard there, for reasons I'm not exactly sure of, but it's pretty close. Okay, so let's exit out of this and save it. And now we'll try to run it and see, hopefully it'll show up on the OLED. So very simple wiring, and I have more wires than I need here. Here's our OLED, and when I started setting it up, I was going to use my smaller OLED, but then the messages got crunched. So got this too close, so I had to slide it over here, and that's what these guys are. These are just jumpers over to this, because originally I wanted to put this here. Ground and VCC, and then SDA and SCL going to the I2C3 bus on the LuckFox, which is the same one we've been using all along in this series. Okay, so let's go ahead and try to run this. So sudo python 3 ISS speed, and boop. Got a error here, so I will pause the video and fix that. Okay, I make this mistake all the time, and so maybe it happens to you too. So just to go over this, so when I pasted this, the names of the files gets pasted down here. So we need to go into, make sure that doesn't happen. And probably if you're better at cutting and pasting than me, then it didn't happen. But I'll show you where it happens in case that does happen for you. So when we grab all of this, I never catch this, that this also gets grabbed up here. So this gets pasted at the bottom. So we really have to make sure that we back off on that, or on our highlighting, or catch it when we plug it into our, when we paste it into our program here. So this should fix it. And now we'll do, now we'll run our program. And we see here, I'm going to turn the camera and try to get it. Autofocus here. There we go. Okay, so we can see we're printing out our values on the screen here, and we're also getting our values printed to the OLED. Notice our speed, 24,850, is about 1,000 kilometers off of what our predicted is. This will vary up and down as we were looking at it. So we see here it's kind of climbing, so it'll kind of climb and fall rather substantially, maybe about 1% of the total. And that does that kind of slowly over time. All right, so this is the API call. You could, if you were doing some things where you needed to track, let's take this International Space Station as an example, like you wanted to try to catch it at when it's overhead. You could have it the LuckFox send a little alarm or give a little alarm when the position is getting close to your area. All sorts of things that you could do with this. Other APIs include weather. So there are, I think, numerous free APIs out there to gather weather information, air quality information. So a lot of the environmental information might be available as well. So this is how we do it with the LuckFox.